everyone. In this video, we are going to learn about the Fermat's little theorem and the applications of the congruence modulo M. I will explain what this theorem says and how to use it and solve a few examples. Fermat's little theorem. It states that if p is a prime number and a is an integer that is not divisible by p, means p does not divide a. In that case, a raised to power p minus 1 is always congruent to 1 mod p. Firstly, let's understand what does it means using an example. Suppose we have a prime number p is equal to 3 and an integer a is equal to 4. Does 3 divide 4? No. It means we can apply the Fermat's little theorem. According to this theorem, 4 raised to power p minus 1, that is 2. This is always congruent to 1 mod 3. Let's check it whether this is true or not. By the definition of congruence, 3 divides 4 square minus 1. That is, whether 3 divides 16 minus 1. That is, whether 3 divides 15. Or we can say that 15 by 3. Is that exactly divisible? Yes. It means this is true. We can also check it with the help of remainders. 4 square, that is equal to 16. 16 when divided by 3. Is the remainder is 1? Yes. If the remainder on both sides are same, when divided by the m, or we can say 3, then it means numbers are congruent to each other with respect to mod 3. So the theorem is verified for this case. Now, can we take p is equal to 4 in this case? No. Why not? Because it is not a prime number. Hence, this theorem is not applicable for the composite number. Now, let's take another prime number. P is equal to 7 and a is equal to 2. Check it whether the theorem is applicable in this case. First thing we need to check it whether 7 divides 2. No, because 2 by 7 is not an integer. So we can apply this Fermat theorem. According to this Fermat theorem, we have 2 raised to power 7 minus 1, that is 6. That is always congruent to 1 mod 7. It means when 2 raised to power 6 is divided by 7, the remainder is 1. Whether this is true? So what is the product of this? 2 into 2 into 2 is 8. Even in this case 8. 8 into 8 is 64. 64 when divided by 7, is the remainder is 1? Yes. So Fermat's theorem is applicable in this case. Now let's use this theorem to solve the particular examples, that is an application of congruence modulo M. The first example we have, find the remainder when 2 raised to power 50 is divided by 7. It's very easy to answer this question. First step, we need to think whether we can apply the Fermat's theorem or not. In this case, we are dividing by the 7. Is 7 is prime number? Yes. So in this case, we can take p as a 7. Now identify what is the value of a as per the Fermat's theorem. We need to divide this number by 7. So base is 2. It means a is 2. Now check whether p divides a. No, because 7 does not divide 2. Now apply the Fermat's theorem. According to the Fermat's theorem, a raised to power p minus 1 is congruent to 1 mod p. It means a is 2. 2 raised to power p minus 1, that is 6, is congruent to 1 mod 7. Now we have 2 raised to power 6 in this case, but we need 2 raised to power 50. In the next step, divide 50 by 6 and find the quotient as well as remainder. Quotient is 8 and the remainder is 2 because 6 into 8 is 48 plus 2, that is 50. In the next step, we can take both sides as the power quotient. Quotient is 8. So what we can do? We can take the power 8 on both sides. Here we have 2 raised to power 48. On right hand side, 1 raised to power 8 is 1 mod 7. With the help of Fermat's theorem, we get what power of 2 when divided by 7, the remainder is 1. Once the remainder is 1, it is very easy to answer this question because we can reach near to this number with the help of this power. So we can find the multiple of 6 near to the 50, that is the 48. So we can increase the power 8 on both sides. On the left side we have 48. On right hand side it is same as a 1 because 1 raised to power positive number is 1. Now we need 2 raised to power 50. In the next step, multiply both sides by 2 raised to power 2. Because we can multiply both sides with the same number. On the left side, we have 2 raised to power 50. On right hand side, this is 4 mod 7. Now look into this equation. 2 raised to 50 that we needed. Mod 7 as it is because we are dividing by the 7. Here we are getting a 4. Now is 4 is a remainder, or we can further simplify it. Simplify it means, can we divide this number with the 7? No. So ultimately, this is the final remainder we are getting in this case. So here we can say that the remainder when 2 raised to power 50 is divided by 7 is 4. In this example, we have basically used the two results. The result were, if A is congruent to B mod M, then the first result is we can take the power n on both sides. Second result, we can multiply both the numbers by the same integer, where n and k are the integers. Now let's take another example. Find the remainder when 2 raised to power 402 is divided by 4. Notice here the divisor in this case is 4, which is not prime. So we cannot use the Fermat's little theorem in this case. So how to proceed in this case? Here we are dividing a number with 4. So we take mod 4 and we need 2 raised to power 402 is congruent to what? How to answer this problem? In this case, we can proceed with the manual power of the 2. It means 2 raised to power 1 when divided by 4, what is the remainder? Just write the remainder in this case, that is 2. 2 square when divided by 4, what is the remainder in this case? That is 0. 2 raised to power 3 when divided by 4, remainder is 0. Now you can observe between this equation and this. 2 raised to power 2 when divided by 4, remainder is 0. When we are increasing the power here, basically we are multiplying both sides by 2. On the left side, power is increased. On the right side, it is always 0. Or we can increase the power of this one. This is 2 raised to power 201. That is always congruent to 0 raised to power 201. As it is a finite number, here we have this is congruent to 0 mod 4. Or we can say that When this number is divided by 4, remainder is always 0. Taking the next case, find the remainder when 7 raised to power 52 is divided by 11. In this case, we are dividing this power by the 11. It means we are dealing with the prime numbers. Now, as per this, we need to find 7 raised to power 54 is congruent to what number? Mod 11. Can we apply the Fermat theorem in this case? As P is 11, which is a prime number, and A is 7. Now we just need to check whether P divides A, or we can say that 11 divides 7. No. So P does not divide A. It means we can apply the Fermat's theorem. So according to the Fermat's theorem, A raised to power P minus 1 is congruent to 1 mod P. So A is 7. 7 raised to power P minus 1 is 10. This is always congruent to 1 mod 11. Next, we need to increase the power and we need to reach at 54. What we can do? We can take power 5 on both sides. On left side, we have 7 raised to power 50 is congruent to 1 mod 11. Now we need to reach at the 54. So multiply both sides by same number, that is 7 raised to power 4. On left side we have 7 raised to power 54. On the right hand side we have the number 7 raised to power 4 mod 11. Now there is no need of the calculator in this case. It's a very simple to answer this one. What we can do, we can write 7 into 7 into 7 into 7. As we are dealing with the mod, it means we are dealing with the remainders. So 7 into 7 is 49. Here again 49. Now think 49 when divided by 11. What is the remainder? So in place of that, we can keep that remainder. 49 when divided by 11, the remainder is equal to 5. So here we can write this is congruent to 5 into 5. Now 5 into 5 is 25 when divided by 11. So 25 when divided by 11, remainder is, that is 3. So we can say that this is congruent to 3 mod 11. It means 7 raised to power 54 when divided by 11, the remainder is 3. Let's take this example. Find the remainder obtained by dividing this sum by the 12. Now we have here as a factorial. Do not worry, this is very easy question. We just need to figure out 1 factorial is equal to what? 1 factorial is 1. 2 factorial, that is 2. 3 factorial, that is 3 into 2 is equal to 6. 4 factorial, that is 4 into 3 factorial, or we can write 4 into 3 into 2, that is 24. 5 factorial, that is 5 into 4 factorial, and we can split this one as 5 into 4 into 3 into 2 into 1. Similarly, we can write the other one, but there's no need to write the other one. Why? Because these three numbers are not exactly divisible by 12, as the numbers are less than 12. It means in this case we can keep this as it is. 4 factorial when divided by 12, that is equal to 24 by 12, and in that case the remainder is 0. Here we are just writing the remainders. And when we have 5 factorial, as the 4 factorial is divisible by 12, it means 5 factorial is also divisible by 12, and in this case the remainder is 0. Similarly for the 6 factorial, 6 factorial can be written as 6 into 5 factorial. As the 5 factorial is exactly divisible by 12, as the remainder we are getting 0, It means x factorial is also divisible by 12. It means rest of the factorials when divided by 12, the remainders are 0. So overall sum in this case we have 9. And 9 is not divisible by 12 and it is also less than 12. So we can say that when this number is divided by 12, the remainder is 9. So this is the application of the congruence modulo m. We can find the remainders with the help of congruence modulo m.